how we deploy, or I guess the engineering specific usage of on-drilling tools, whether it's rotary steerable or well. I work in conjunction with our bid group so that when we get called out by an operator, we use our tools properly and with our bids to drill wells. I think actually about 50% of my job I see us support doing sales. So I go to a lot of client offices, speak with people, show them what we can do, what our pricing is, and whatnot. This is very different for me. I'm more used to working with 10 or 12 people, dollars and cents, and what we can do for our customer. So, like I said, it's different for me, so don't hesitate to jump in and kind of be back up. So before I worked for Baker Hughes, I worked for Jerde in Arkansas. I was an MWD building tools, or I guess the survey tools, formation evaluation was used to evaluate the water steel. Now with that, this presentation will cover what you see up there. We'll look at a brief overview of directional drilling industry, particularly in the U.S. Give you a time frame of how things have changed from
Thank you.
college and stabilizers to compression of utilizing MWD tools, LWD tools, motors, and eventually rotary steerable. We'll review a little bit of the basic aspects of drilling, how it affects your well bore, how you build the brakes, and so forth. And then we'll get into the rotary steerable presentation. My knowledge base is in Baker Hughes' rotary steerable tool, which is called auto drill. But in this presentation, we'll cover the competitors, which include Halliburton, Jerde, and Weatherford. I think there's a path on your slide here as well. So, warn you ahead of my knowledge on those tools, just because aside from the auto track, I have limited experience with Schlumberger's tools as well. So, forgive me where I do not provide that information. Any questions so far? That is more basic stuff probably that we covered in 100 level class or 200 level classes. Why do we drill? Well, to get oil and gas. What are the main objectives? I can tell you from an operator perspective, because this is how we sell, is you have to do it safely, you have to maximize your investments. Meaning, they're paying the money to us, a service company. We have to be able to hit their targets, hit the reservoir, get oil and gas, or whatever they're trying to draw out. And most of all, safety. I don't know if any of you work in the field or how they presented it at the machine, but safety is imperative. I still go into meetings with VPs of Exxon, and before we talk about anything, we have a safety note. We'll sit down and cover where the cases are in the building, if something goes wrong, what to do, so on and so forth. So safety is paramount, and as you guys move into the professional world, make sure you keep that at the front of your mind, because if you're in the field, nothing's worse than losing a person or losing a limb or something bad happening. And on top of that, if the superiors see you do that, they're going to hold you higher regard. So safety's key. Keep it at the front of your mind. It'll help your personal life because you won't die. It'll help your professional life if people respect you. Okay, so way back when we drilled vertical holes. Our first oil well was ever drilled was in Pennsylvania. Then we had a huge find in Texas, and in the 1930s we started drilling in Long Beach. Now what you see here is what now is residential, commercial, and so forth. These are all vertical wells with straight dumb iron derricks. They were drill straight down, oil would come out. They actually discovered this field when they saw oil washing up on the beach. It was early 1920s, they saw it and they started developing this thing. So how the vertical wells, not very efficient. You can see there's a large footprint, and on top of that, you don't get a lot of reservoir draw comparatively if you go straight down. So over the years, we've gotten to what you see there. Is due to California regulation, we've reduced it to those 5 sites you see on the circle in yellow on the board. One pier, rig site, and then 4 other platforms. This is called Promise. I'm sure some of you have heard of it, not all of you. And Phelps has become it's kind of the testing ground for most advanced directional drilling globally at this point in terms of well complexity. So you can see all those lines up there are the different well bores that have been drilled, and before the downturn, those are increasing every day. Due to the fact that that field, I don't know the technical term, but there are a lot of different pockets and a lot of different areas that hold oil. And they're so rich in their hydrocarbon content that it's worth drilling like this. So they'll hit targets roughly the size of its desk because they can draw that much oil. So, due to the fact that we have well bores this complex, there's that many well bores, we have to come up with better technology in order to hit those targets for our client. We're trying to get maximum draw out of it. So here are different well profiles that have developed over the years. There's J, S, and horizontals. Those, as you guys move through the industry, everybody will have different vernacular for how they describe those. We call them laterals sometimes, meaning drill down, drill your curve, your double grade that your professor described earlier. Drill in your lateral, reach your DE, and then frac. So depending on what you're trying to do, you'll have a different profile, whether you have to make it across lease lines, you have to drill to a certain target due to the fact that your rig's in one location and you to another. You have to absorb these different types of profiles. These different profiles may even be utilized based on what your goal is in terms of what you're trying to draw out. If you look at Wyoming and the gas fields, they did a lot of S-type wells because that profile draws out the most gas at this point with our third technology. Now, what we're doing in the DJ Basin, Williston, Powder River Basin is really longer and longer laterals. Those are sometimes called J-type wells from what I've heard as well. So, there's different well profiles depending on what we're trying to achieve. Here's some more examples of those different well profiles. These are actual plots that we pay for use as provided for what we drill for clients. We recently did a well in the Powder River Basin last year where we drilled below ourselves, wrapped around ourselves, drilled the curve, landed it, and then drilled a 2-mile lateral. So it's just, there's a lot of different factors that go into drilling this type of well work. But it will come up at some point. You guys will be going into technical drilling, you will see this, and it's just based on what your operating is being based on. Whether they're trying to get for their investment or regulation or other stipulations that cause them to have more functionality. Now, like we said at the beginning of the presentation, this is a brief, not very detailed overview of how directional drilling has developed over the past century. You can see that we, like I said earlier, they were drilling just rotary, spun Kelly, you drill straight down where the bin ended up and look at oil, basically. Then we started getting surveying tools so that we could use correlations and understand what oil was on. Schlumberger was one of the biggest drivers of that in the 1920s. They developed the wireline tools, which eventually led over into LWPs and MWPs we have nowadays. Now you see it as it progresses, we got into downhole motors. Downhole motors is an extremely broad concept. There's a lot of different words for it. There's positive displacement motors, there's turbines, there's turbines. There's a lot of different things, and that technology can be configured so many different ways depending on what you're trying to do as a configuration. In Russia, they use turbines, which spin a bit so fast, a diamond imprint bit so fast that it just rubs the rock because it's so far that's what they do. What we use here in the Rockies is your positive displacement motors, which are high torque, medium low speed on a world scale, if you will, that are behind a PDC or tricumpanator that are used before. Then we got into our MWD technologies. That is basically where you put it, if you guys don't know, if you touched on it. It's basically a tool that tells you direction information and some basic measurements like vibration, and then transmits it up electrically. The transmission or telemetry modes are different depending on where you're at. You can have live poles, you can have electromagnetic, you can even have drill pipe wiring. Just depends on what technology you have or what you're willing to pay for. So then we get into steerable motors, but still downhole motors. LWD, that's when we started to understand our, it's essentially wireline field lines. So the way it worked is that Jerde was the leader in developing wireline, and everybody started to catch up. And that's when they got tools like the density measurements, porosity measurements, mobility measurements, temperatures, viscosity measurements, more than I could ever name. And once they could do a wireline, they realized they could mount that technology in collars and started moving into they had that and it's theorized that a lot of wireline in the next 20 years will go away. I don't know if it's true, and we'll get pretty much everything going on tools due to the fact that they're leasing a rig on a day rate. There's no point in taking extra time for wireline money if you can log it and that way. I know some states have stipulation that you have a wireline due to the fact of data quality, so it just depends. But from what I've seen, LWD becoming more and more prevalent. Then there's that wire pipe that I started talking about. They use that now to see a lot. Basically is modular connections through your drill pipe that allows you to have huge amounts of data transmitted on a whole lot. Can be problematic due to the fact that if your connections aren't good, you can get fluid ingress, you lose your connection, and you have downtime, and you have to drill out. And then, what I haven't had a lot of exposure to is the seismic while looking ahead. They call this geostopping or geosteering. It's not just seismic. You may use resistivity measurements, you may use cruising measurements. It just depends, but it's basically what operators are looking for more and more, especially in exploratory wells, is being able to understand data as close to what so that you know if you're going into a formation that you don't want to go into, you're going to hit a fault, or you're going to hit a fracture hole. So it just depends. You want as much information as cheaply as possible, as far as possible. I'm speaking from the operator standpoint, the service standpoint. I want it to be as expensive as possible. And so on and so forth. And that's something I should have said earlier, guys. I come from a service background. So I worked for Schlumberger and Baker, Good and Halberts. I work with operators, so there's two different paradigms that we work in. I want to give you what you want for as expensive as possible. That helps my bottom line. The operator wants it as cheap as possible because it helps their bottom line. So I'll keep on jumping back and forth from my knowledge. If you have a question on that, maybe that's more of a presentation, but yeah, I'll try to give you information on that as well. If there's any other questions, feel free to ask. So talking to Lee, he said you guys covered this more or less on inclination and azimuth. Inclination is basically how many degrees you use for vertical. So typically when you drill horizontal, you start at 0, you drill down 1,000 feet, you build your curve at a lower rate. Currently in the Rockies, the magic numbers are anywhere from 8 to 12. You get to that 90 degrees inclination and you drill backward. So 0, and then azimuth, you guys know what the compass is, 0 to 360, 90 right. I guess 90 degrees is east. 370 is what I'm saying. So those are the two main measurements we use to steer. There's numerous others that go into it, such as formation depth. That's all I can do right now. But yeah, so there's other measurements, but those are the key directional measurements besides that. Okay, now influences on bid trajectory. We'll get into very basic mechanics of direction. This slide right here shows you the different forces and contact points that affect how you're going to be able to steer. By steering, I mean your bid deflection. There's multiple bullet points up there that tell you what goes into how you can affect how you bid. Weight on bid, drilling parameters. Like drilling parameters, that's flow, differential pressure, rotary speed, and whatnot. And then we get down to stuff such as your PHA configuration, where you get stabilizers, how long the stabilizers are, your bed housing, when you're in the mud orders, and so on and so forth. Now these basic mechanics right here are what we use, or what we have used to develop our motor designs, our vent housing motor designs, and our rotary steer designs. It's all about contact and contact forces. And that's across the board. In a very small nutshell, this is what it was about. If anybody have any questions on that, want more information? Now we get into steerable motors. So Lisa, you guys have a little bit of exposure to that. So this is what you're seeing is the vapor-fused positive displacement motor. Drilling fluid pumped down the annulus hits that power section, which is your rotor and your stator. The rotor is that silver shaft, and that rotates counterclockwise. It's counterintuitive. That rotates counterclockwise in order to rotate the bit clockwise. So think of a bar something like that. So that rotates within the stator, which is a metal can that has a contour elastomer. And the faster you pump, the faster that rotor goes, the faster the bit goes. So the fluid goes into the power section, which is that rotor stator configuration, generates torque, transfers that torque through a drive shaft to your bearings, and then to your bit box, which rotates it. The basic idea of a motor, besides steering, is to give you extra bit RPMs and extra torque. So aside from when you're just generating your top drive, you're actually getting mechanical work out of your fluid system. So when we started using motors is when we went from Kelly brakes, creating all our torque, essentially all our NSC or mechanical power to drill, and then we started to factor in the use of hydraulic work. So it was actually a big game changer because of the fact that we have a whole other input of power in order to drill. Now 5.6, if you guys go into the drilling world, there's a bunch of different configurations. There's 1, 2, there's 7, 8, there's 4, 5, whatever. It's always n minus 1 for that. That basically is the comparison of it's your load configuration. So your rotor loads to your stator spots. Yeah. Or vice versa. So you get it's basically your configuration for stator rotor. Now the idea behind that is that in different configurations, you start to be able to relate power, meaning torque, or torque power, whatever you may want to be. You also relate torque cost, and then your bit speed. So a lot of times when you go up, you have a higher load configuration like a 7.8, that will generate more torque than a 1.2. But your 1.2, which is essentially going back and forth in that stator can, has a much higher bit RPM. So it depends on the formation you're drilling. If it's a very hard formation, where you have to use a diamond intake bit, drilling really slow, you a lot of times want a very high bit speed because you're essentially rubbing away the rock. A lot of shale drilling, what we're doing now is you want very high torque with the PVC bit, where you can put a lot of weight on bit, dig in hard, and you get a lot of torque generated by that power section in order to cut out that rock. This shows you the geometry. Now this relates to a few slides back of when we said factors that go into your steering principle, the contact points and contact forces. This shows you what we call 3-point geometry. This is how pretty much all motors are designed. All motors are designed based on this principle. Now the 3-point geometry directly relates to how you can generate a bill, or your pillar, or your motor body, or your motor bill. There's a bunch of different terms that won't be the same. It's the degrees of inclination change or azimuth change per 100. Basically how much you can turn. So the 3-point geometry, you can see those 3 bubbles separated by L1, alpha, and L2 are the different contact points of the motor. So you can see the equation on the top right, pretty simple. You work with those different factors, change your motor length, change your alpha, which is your AKO setting, and you can get different building rates. Some situations you want a very high building rate. I can tell you we're drilling in the San Juans and we're going anywhere from 20 to 30 degrees per 100 foot building rate, which is extremely high. Coiled tubing goes even higher than that. There's other areas in the world, including the Rockies and Southern Wyoming, we drilled places where 2-degree buildup is high. It's just based on what your goals are for the well and what you can do with the current technology. So aside from this 3-point geometry, that's not the only thing that influences the build-up rate. You saw in previous slides, it can also be parameters you run, your bit configuration. The formation is a huge factor, the whole formation push. Mechanically, I can't tell you exactly what formation push is. It's technically a phenomenon, but it is essentially the formation using a force or behaving in a way that is or turn rates. Now, Lisa, you guys have some exposure to rotating versus sliding. Sliding, as you know, is when you keep the drill straight constant. You get a tool face alignment, meaning you get an idea of where your high side is or where your bend is. And then you pump on the motor to create bit torque and bit speed, and you drill and deflect in that direction. Rotary drilling is when you do this. You don't have a tool face. You basically, you rotate your drill string and you pump on the motor. So you have a higher bit speed, a higher bit torque, and you drill ahead. So this is usually for making a hole when you know you're going in the right trajectory. Sliding is for building a curve, deflecting, getting away from vertical to separate from boulders. Does everybody know what tool face is? Yes, no? Okay. Differences, two types of tool face. Magnetic gravity. Yes, no? Okay, so magnetic more towards vertical, small nutshell. Gravity is once you're above 35 degrees of elevation. Gravity is the most common. So, rotary and slide drilling. Right off the bat, what do you think the drawbacks of this having these two drilling modes? What do you think happens to your ROP when you're sliding? Think it's more or less than when you rotate?
Less.
Exactly. Okay, so there's the first aspect of where you lose time. You get lower ROP when you're sliding. Where else would you lose time? This is more specific to people who worked on the rig or
When you're setting your tool face, trying to get that torque code string.
perfect. So when you're rotating, you basically tell your driller, hold this differential pressure by this weight on bit, pump on the floor this rate, and spin it out. And you drill ahead. When you're sliding, your directional driller should go to the rig floor and align it tool face, meaning I want 100% drill, so I'm steering at 0, and they slide at that lower RP. Now that's all time you lose to not being pulled. So it then essentially adds time to the operation. So you have lower RP with sliding, and you lose time to the actual starting the slider or aligning the tool face and being ready. What's the other problem with sliding? Slides. If you're having slide rotate sections, what do you think it does to your wellbore?
Differences in diameter.
Do you know what the technical term for that is?
Say tortuosity.
Tortuosity.
Perfect. Tortuosity. So you create tortuosity. Now tortuosity, it becomes more and more of a problem as we drill further. Continental is currently drilling the longest wellbores in most of the basin. They're drilling 3-mile laterals, so 15,000 feet. And that's 15,000 feet in the lateral. They have to drill down to about 10.5 before they even go into their lateral. So they're having 25 to 27,000 feet wellbores. Now, if you have one curve in that wellbore, and there's a bunch of slide and rotates that induce a lot of tortuosity, what do you think that does to your torque and drag? Especially as you get further down. Exactly. Can't be the way you get. So it affects your joint. And we'll get into that a little later. And all this I'm feeding you because then that will lead into why we have rotary steerable and benefits of it. So as you stated here, that's where you can see the tortuosity where you have your slide and rotate section. Typically, depending on your drilling program, you may slide 30 feet, rotate 10. Or vice versa. It just depends on what your tendency is and what kind of build rate you're using. So you have your slide rotate sections, and that induces tortuosity, and it causes you to lose time. So there's two factors that you want to eliminate in order to stay. Now, it'd be perfect for me, it'd be really good for my wallet if we did everything rotary steerable. steerable is a lot more expensive, we make a lot more money off it, but we still do use motors, especially in the rockets, that's the primary technology. Offshore, Saudi Arabia, that's 70–80% rotary steerable. But that being said, I have to tell you the pros and cons of rotary steerable. In a lot of applications, rotating with the motor is faster. The other thing is with rotating faster with the motor. Rotating with the motor is faster in a lot of applications. Higher ROP. That being said, some of the cons of using a motor, or cons of using rotary steerable compared to a motor is that there's less liability with the motor. There's no real high-end technology. That's not an expensive piece of things that will work for you. If you go into rotary steerable, we charge these things. We have charged these things higher than $40,000 a day, and if you lose it down the hole, you have to pay a $2 million ticket or bill if you don't have insurance. So, that being said, you got to evaluate your drilling program, and if you're doing an exploratory well where you think you got slumping or pack-offs or differential staking, and there's a chance of losing or severely damaging your PHA, it can be a lot more advantageous to use your motor assembly because there's less risk and less money. But at the same time, as you develop that field, maybe you know that rotary steerable can be a better option, faster drilling, so on and so forth, saving time and saving money. Any other questions at this point? Okay, now we'll get into the rotary steerable. Sorry, I hate the multiple times. I said in my presentation. By the way, since the downturn, we used to bring in the technology manager for North America, I think the world, to speak to you guys. Now you get me. So sorry about that. Times are tough. So now we'll get into rotary steerable. You can see the green line shows you how much more smooth your well bore can be by using 100% rotation, meaning we take out the slide section. Now there's different mechanics to rotary steerable that we'll get into, but it basically allows you to rotate 100% of the time due to the fact that you have a certain steering mechanism right behind the bit that allows you to meet your trajectory that you're planning for trucking. The higher end rotary steerable tools, which I will tell you Baker Hughes has, will give you what we call a gun barrel bore hole. Sorry, it's a tongue twister, but we call it a rifle barrel because it's so straight. Due to the fact that what we've done with our steering mechanics and the algorithms we use to operate our steering systems. Very complex stuff. I don't know a lot about it because I'm not part of that group. I'm also using it, not the side of design. But as technology has progressed, we've gotten more and more exact steering abilities, which is very desired by the operator due to the fact that they're getting more and more difficult. They're getting more and more difficult targets, and they're getting closer and closer to the world, which is, you guys will be exposed to that a lot if you haven't already. You just get that collision. So this basically explains and shows you, we touched on it previously, but it explains, what rotary steerable does. Gives you some movable, we touched on, it's pretty straightforward. Yeah. Sorry, I don't have much more on this. I'm trying to think if I'm missing. Now this is a timeline of how Baker Hughes developed our rotary steerable tool. You can see up there the different dates. It started over 20 years ago. Huge amounts of money are poured into by the service companies developing these tools. I can tell you the biggest investors of their technology is number 1 Schlumberger, number 2 Baker, number 3 Halliburton. Now their $500 million R&D budgets don't go just to drilling, but it goes into numerous products, whether it be packers, their cement designs, whatever it may be. But there are huge amounts of money that are poured into developing the rotary steerable tool. And you can see it's done over a long period of time. I can tell you even now, since I've been with Baker, which has been 40 years, I've seen 3 different iterations of our rotary steerable tool, and all the competitors are doing the same thing. bear with me. If you have any technical questions, I'll ask you after. But
At Baker Hughes, the key component in every one of our AutoTrack systems is the steering unit, which directs the wellbore with unmatched precision and accuracy. The AutoTrack steering unit incorporates 3 expandable steering ribs on a short, slowly rotating sleeve. The ribs apply carefully calculated forces to the borehole wall to deflect the bit and steer the well. The sleeve, which is only 4 feet long, is mounted on rugged, mud-lubricated bearings and is engineered for enhanced performance and reliability with no rotary seals that could restrict tool life. Electrical power and data are transferred from the rotating drive shaft to the sleeve via a wireless transmission system. A highly accurate 3-axis sensor package, located only 3 feet above the bit, constantly measures inclination and tool face orientation. The sleeve's closed-loop electronics continuously compare these measurements with the desired target and adjust steering parameters accordingly to ensure precise well path control. To keep the well on the desired path, 3 independent hydraulic ribs expand and apply a precise deflection force to the borehole wall to steer the bit. Each rib is continuously adjusted to achieve a constant steer vector, regardless of the sleeve position. The ribs can be fully retracted during tripping or reaming operations. Inclination and other sensor data are transmitted to surface, allowing field personnel to monitor tool operation and react immediately to any changes in downhole conditions. The AutoTrack steering unit, rugged, compact, and reliable, delivering precise wellbore placement for improved drilling efficiency and increased hydrocarbon recovery. Our AutoTrack system drills the industry's most precise well paths using a slowly rotating sleeve containing 3 steering pads. The sleeve incorporates tool face and near bit inclination sensors to constantly monitor wellbore position.
So this is usually in the presentation where we ask you if you want to buy one. But as you can see, it's very lightweight and heavy. That's actually the older iteration of the AutoTrack tool. Now we have circular, force for higher buildup rates. It's shorter. We added more sensors, and we added more algorithms to steer better. In a nutshell, what we have in the past 4 years back. Now this relates to a number of slides earlier when I explained what mechanics have a bit behind the big one, the directional deflecting. Now we're going to focus on the bit and the contact forces itself that lead into how we use our steering mechanics in rotary steerable, whether it be with Baker, Schlumberger, or Howard. So you can see there's a side force acting on the bit if it's deflected. We call that side cutting ability. That's basically how well you can cut relative to your face. In the early days, you only cut one direction, that was forward. Now we're designing bits with gauge cutters or gaugers around the side that allow us to cut left, right, up, or down due to the fact that the cutting structure is in that area and we can exert force with our rotary steerable tool. Now there's the bit tilt angle, which is basically, and that's easy enough to understand, is which way you're pointing it down hole. There's a little bit of room down hole for you to move your bit. It's not just like it's always locked in. You can move it a little bit in order to help those side cutting abilities and reflect that. I'm very one-sided. I work in drilling. I work with bits. Bits is a whole different world. We work together. We sell a lot working together because we compare our technologies. But there's about 1,000 topics we could talk about with the bit itself. Whereas those other 1,000 topics that focus on the common system, which is the rotary steerable. So I wish I had a big guy here with me. But just for your knowledge, there's a lot more than just this rotary steerable tool, whether you think I'm talking to you because I'm talking to you like that's what it's all about, because that's what I know. That's a huge market, but you have to understand there's a whole bit and probably even more science and technology on that than what we have. So, that being said, here are the 3 broad areas that rotary steerable tools are designed under. These 3 different steering modes for mechanics. You can see the top one is what we have with big use. Now, we call it push the bit because due to the fact that, as you saw in the earlier video, those pads push against the borehole wall and push the bit in a direction. You can see the red arrow is where the force is being exerted by the tool. You see that for all the different gravities. And then I believe the blue arrows are the resultant forces, meaning where your cutting action is happening in the bit. So you can see with the Halberd, Geopilot, Jerde, MMS, the Schlumberger Power Drive Exceed and Archer, they have point-to-bit technology. So they adjust bit tilt down hole. They use different mechanisms, whether it be flexing a shaft or having it's essentially an adjustable AKO down hole to where they're pointing the bit in the direction instead of pushing it. There's a lot of different applications and pros and cons to each type. Some are more robust, some are less robust, some work, some don't. And then it really depends on your bit, where you're drilling, what you're trying to do, and so on and so forth. I can tell you our auto track tool, our larger tool sizes, are for high dog lengths. We want to drill curves. Schlumberger is the other big competitor in the market right now, where they can drill high degree bends as well. By high dog leg, I mean 15s, 12 to 15s. That's in the rotary steerable world, that's your higher. Like I said, you can get to smaller tools and coil tubing and get very small units that can do 20 plus, but the grand scheme of things, 15 is high. Now you can go with Weatherford, Halberd, Pathfinder, there's another, Terravici. These all do the lower dog legs, which are used a lot more offshore. And the third mode I don't have a lot of education on. I learned a lot about the second mode when I was with Schlumberger. I focus on the first mode now. The third mode is not very common. We directly competed with Weatherford last year in the Jonah field. Went well for them, or went bad for them, went well for us because they failed. We did essentially a drill off, where they used their rotary steerable, we used our rotary steerable. In that situation, there didn't work hard to get. Go up to Canada, Weatherford is probably the preferred directional drilling company there, and their rotary steerable is utilized quite often. Pathfinder, for a long time in the US, they were the preferred market. Their rotary steerable tool, I don't know much about, I'm sorry. Any questions on any of those?
Is Schlumberger still using the Power Drive Exceed? Seems like they phased that out, I thought.
So, they are. What's interesting about that is Schlumberger is the best at branding, if you will. They're the Apple service companies for directional drilling because they do it so well. They'll say Power Drive Exceed, Power Drive Archer, Power Drive whatever, and then they'll cut that out and say Archer something. It all comes from 2 basic technologies, point the bit, or push the bit. What they do is they either add mechanical force to their steering unit, or they'll put a motor behind, which we'll get into later. But it's not, you're right, they have moved away from it, but it is used in certain parts of the world if people don't want the high-end stuff and they want some lower end and it's application specific. So, it is still used. The weird thing that's going on right now is, so when these rotary steerable tools are so expensive, but they're so capable, and when the operator wants them, they'll pay a lot of money for them. So you use that in business situations for leverage and upselling. Now what I mean by that is that you go to an operator, whether it be Shell BP or a smaller player like Whiting, Sandridge, whatever it may be, and they say, we're going to pay you so much money to use your rotary steerable tool. And you always want to go, for the most part, hey, you have to use our directional services, which will cost this much more. Meaning, we're going to send our personnel out. We're not going to rent you to do it. There's a whole rental business for motors. And what Schlumberger now is doing with their older steering units, or their older tools, is they're renting them out, which was never done before in the directional drilling world with rotary steerable tools. finding out they can send this asset out, beat it up because it's old and it's not their prime one, but still make a little bit of money off it. Especially in these times, that's huge due to the fact that helps you get it off your book, and you do get some revenue you can mark down. And which I didn't know was part of the game. Excuse me, I'm a little more callous. I always thought of stuff in terms of revenue and profit. If you have negative profit, you cut people, you cut personnel, you make cuts. What a lot of companies are doing now, probably very fortunate for me, is yeah, you may be operating at a negative profit, but you still are drawing revenue. And due to that fact, you can keep more personnel on in your company and in your area. It's very complex, especially with these multinational corporations, but I probably got a little bit past the whole question itself. But in a nutshell, there's still nothing revenue now. It's unorthodox from what we see in the past. Now we'll take a quick or a more in-depth look, not very in-depth, for the different competitor rotor steerable tools. I gotta be honest, I didn't want to add this in there, but I still run my hand. I'm used to doing sales presentation, so I'm never gonna touch my competitor, but I'm gonna do it today. So we're gonna look at the competitors, meaning Schlumberger, Weatherford, and Halliburton, Pathfinder, something like that. So this slide will show you Power Drive Archer. Power Drive Archer is our main competitor now for those high oscillation wells, meaning up to 15 degrees. We have a tool, it's called Auto Track Curve, that we can do directly with this, and those are the only tool on the market for this specific application. That application, like I said, they will build great wells. Tool sizes they offer in this is 4 3/4 and 6 1/4. So you can essentially use this anywhere from a 5 7/8 inch hole to a 6 3/4 hole for the 4 3/4 inch tool size. And then for the 6 3/4 inch tool size, you can use that for an 8 1/4 inch tool, 8 1/4 inch hole up to a 9 5/8 inch hole. Does anybody know what that's predicated on? The two main principles of how you choose your tool size, your hole size. So you're never going to use a tool that's bigger than the hole, right? Right? You won't be able to drill. Number two, or not, that's the main idea, but first of all, you want the right tool size in order to be able to generate the torque or transfer the torque to the jig. The second one is fishability. So we actually have a request by operators to use 6 3/4 inch tools in 7 7/8 inch hole. Well, yeah, fit, but if we twist off something, are we going to be able to fish it? So you need some clearance between the hole wall and the tool connection in order to fish it if you have an attachment or anything like that. So it touched earlier in the video, I'll touch on it later with auto track, but this is a hydraulically driven power unit, meaning it's based on the pressure drop behind the pin. There's basically valves that orientate when mud's pumped through it that exert pressure towards one of those pads that allow the bit to be deflected by the force of the pad on the whole wall. Now, for these units to operate, you have to have a bit pressure drop, meaning you have to have a nozzle at the bit so that you have a constriction of flow. Maybe it's not complicated, it's hard to picture, I wish I had a graphic for it, but there are pros and cons to that you do as well. One being sometimes you don't want pressure drop at the bit because your pressure limited on the brake. The other being is this system is more robust than our auto track curve tool. It's less electronics, more robust mechanics, so that when you're in harsh drilling environments, meaning high vibrations, high stick slip, this tool won't break as soon as ours will. Just so you know, if you're going to the field or working in the drilling end, you'll see a lot of failures. Don't get mad at your service company saying, hey, nobody fails, because everybody fails at some point. You know, we're destroying rock out there. We're on a lot of pressure. Here's the Pathfinder tool. Like I said, I'm sorry, I don't have a lot of knowledge. I've only seen the tool once, and I didn't operate it or have anything to do with the operation. You can see the different tool sizes there, as well as some of the benefits or applications and the series mechanic behind it. This is a non-rotating sleeve like the auto track we saw in the video with 3 hydraulic grips that push your bit in whatever direction you're trying to go. Just so you know, Pathfinder was acquired by Schlumberger in 2010. So Pathfinder's technically Schlumberger as well. Cameron's part of Schlumberger. Albert GeoPilot. This tool, I think, is, from when I spoke with operators in various parts of the world, it's a love-hate relationship. We've seen this tool fail after drilling 10 feet. We've seen this tool set records. Some people will pay up the nose for it. Some people will get mad at the service company if it shows up on location. Just depends. I can tell you we have had competition with it in the Rockies. Does anybody know what I mean by the Rocky Mountain, or the Rockies, the area? It's Williston Basin, Powder River Basin, DJ Basin, San Juan Basin, Paradox Basin, Newlands Basin, and then, how would you define Wyoming?
It's a lot of different basins put together. Well, it's Wyoming.
Yeah, and the whole western side of Wyoming, which you asked. So that's the Rockies, even though you're out of place. That's where I focus. That's the Weatherford Revolution is very well in Canada. It's now you can see on the bottom right there, there's a lot of different mechanical components that go into this tool. What you should remember with rotary steerable and drilling tools in general is the more complex and technology driven it is, the more susceptible it is to damage, of course. Do you guys remember the Nokia brick? It's the best phone I think I ever created. I'm bad on phones. I've already broken 3 iPhones. I like them, but I break them. Now the Nokia brick thing was great. You drop it in the toilet at a party and pull it out, right off, you're good to go. Or drop it down some stairs, you're fine. Same thing with drilling tools. Is that yeah, it's more and more advanced, it has all these capabilities, but that comes at a price. A dollar price and the fact that it's not as robust. Now when you have more basic systems like Schlumberger's mastering, you can beat it up a lot more in the more harsh drilling environments around the world. Now we're going to focus on auto track for the majority for the rest of the presentation, and I'm going to give you a better idea of how we steer with this tool. This slide here shows you the steering unit on the top. Now that upper right yellow component, that's the big box. You screw the bit into that part, and then you can steer the steering ribs to the left. Those steering ribs are what comes out of the collar wall and push against the bore hole in order to deflect the bit. Now that's, like the video said, mounted on a diamond bearing pack. And what goes to that diamond bearing pack is a drive shaft that is basically, the drive shaft draws mechanical energy from the top drive and from the motor if you put it on the Jerde, which is the newest way. It's essentially the next step in rotor steerable. Now the bottom left graphic is looking downhole through the steering unit and through the end of the bit. You can see that those 3 pads are all orientated 120 degrees out of phase. And they will push as they slowly rotate. It's supposed to be non-rotating sleeve, but it's actually slowly rotating. And the electronics and sensory tells the tool where each one of those pads is so that it deflects or puts pressure through those ribs in order to deflect the bit in the direction we tell the tool to go. We'll get more into that. Now the basic idea behind it is vector geometry or vector addition, force and direction, in order to have those pads deflect the bit in the direction we want to go based on the commands we're looking to achieve, or based on the commands we send to the tool. Any questions? What time do we go to?
It goes to 10:45.
Same thing, just breaks it down for you in simpler terms. You can see first 50% steer force, that's key steer force. That's the amount of force that is being exerted to deflect the bit. You can see the vector addition, each of the pads exerts 30% of that force in order to have a 100% build, going up, building information. Here's a video that explains it much better than I can. Pretty simple.
In ribs off mode, the expandable pads are fully retracted, allowing free rotation inside the borehole and unhampered tripping or ringing. When the system is switched to an active steering mode, the ribs expand with a low force to stabilize the non-rotating sleeve and centralize the tool in the borehole. Individual rib forces are represented by the green, blue, and red scales. When a command is sent to initiate a change to the well path, the tool's internal electronics calculate the appropriate mix of individual rib forces to achieve the desired steer vector based on the sleeve's current tool face angle. As the sleeve slowly rotates, the electronics constantly adjust individual rib forces to maintain a constant target vector. The target can be changed while drilling via downlink to alter the well path. Note the increased deflection from the borehole center line is represented by yellow crosshairs when the force is increased. Likewise, steer vector direction can also be changed via downlink, as represented by the gray arrow, with the system immediately adjusting the force mix to steer to the new target with unmatched precision and accuracy. Get unmatched well site efficiency and precise well placement for optimal recovery with our AutoTrack service.
Any questions?
You said that communication with that steering pack was remote, you said? Or was it, or you guys run wire connector pipe as well?
No, we do that through multiple telemetry. The telemetry is always, just remember that, it took me like a year to figure this out, or remember it. The telemetry is the mode with which you communicate with your tool. So, mud pulses, we send mud pulses down, we send mud pulses up. Touching on bits once more, it's really important that you get the right bit configuration in terms of the cutting structure and the, I guess, flow regime through the bit, whether that be the nozzle configuration to get the desired pressure drop if it's needed, such as with the shoulder jig tool, and get the desired gauge design. That's usually dictated by the formation. But this is another thing that we focus on. It's a leverage tool. Somebody wants our AutoTrack curve tool, we'll tell an operator, well, you have to run our bits, we're going to charge you. So, there's a lot, like I said, probably more stuff to talk about with this than just the leverage tool, but it's a key component. I work alongside a lot of bit engineers, just to make sure we have optimal performance with our AutoTrack. The bottom left is key. In a perfect world, we would be able to do that. Operators would just give us chunks of money, and we would drill the well for them perfectly. It's not the way it is here for people, our way. But that's key. Try to remember that for you do and what you do. This is the BHA layout for our track. So your steering unit. We have a flex stabilizer. That's based on the steering mechanics we have to use as a contact point, and affects how we can deflect and steer. Then we've got power telemetry. That basically is where we have a turbine that generates power for this tool to operate based on fluid flow, or the drilling fluid flowing through the angles. And then at the same time, that's where the pulser is that sends the communication up hole, and then we send it back down. The turbine actually is part of that communication, because when we send those flow, we call them pulses, or flow, I guess disruptions, pattern flow disruptions down hole, it affects those turbine RPMs. And the right pattern, that turbine picks it up, the tool brains or tool electronics picks it up and says, oh, that disruption or that pattern means you want me to do this. And I'll explain it here. This is the overall system of, this is the system breakdown of what we use at the rig. So on the surface, we use a BPA, a bypass actuator. And this is an automated tool that essentially sends that signal down hole to the tool. The turbine picks it up, understands the pattern, and due to pre-programmed settings, the tool knows what to do. So right now, one of the things people love about our tool is, especially in the lateral, Geology will dictate we have a 91.5 degree dip. We tell the tool hold 91.5 degrees. And this is in the mode, we call this inclination hold. The tool will do it itself, where we're not steering. We just start rotating, start pumping, and the tool does it itself and sends diagnostic back up. And that's what's happening with blue there. The tool's communicating with itself. It's thinking based on its command. It's making those pressure adjustments at the pass to steer as we command. So it's much more automated than it was in the past with mud motors, where you did your slide or your rotating to a survey, you adjust it. Here it's, we're telling you what to do, just drill ahead and give us a diagnostic, make sure you're on track and not broken. And that's what's done with white line, sending that diagnostic up hole. Along with that, if we have LWD tools, meaning density tools, gamma tools, whatever it may be, they'll send that information up hole for geosteering or geostopping. They didn't have this when I was in the field, and this is the coolest thing. If anybody's worked on a rig or you're going to work on a rig, you'd appreciate this type of equipment because it automates the system. So when I was in the field, we had to downlink with pumps. It's still done through the flow system, but when I was when I was in the field, you would be on the rig floor and you have to adjust your pumps in order to have your tool pick up that disruption and flow that's patterned so that it understands the command. Now, coming out of college, it was pretty intimidating going to work on the rig. And you're working next to a lot of roughnecks. And that's a derogatory term because to this day, I'm friends with a lot of roughnecks. I love them. They're great. You know, always have a can or two for you. Great people. I like them. But this guy's, you know, he's the driller. He's operating all the systems. And he's on his clock, a very tight clock, because a lot of these guys get a bonus based on how fast they can carry out their operations well. So you have a little green hat. If you guys go in the field, you probably wear a green hat showing that you're new. They're seeing this little shit, piss ant, whatever you want to be called. That's what I was called a lot. It's normal. You learn to love them. I'm messing with that guy's controls, talking to my tool, and I'm wasting time because they get intimidated, and mistakes happen, or there may be an issue with the pumps, like the dampers aren't charged or whatnot. And you have those issues, and it causes more time and more stress and whatnot. Well, now we have this. It's called a BPA bypass actuator, and we hook it up to the flow line, and it does it for us. This is hooked up to a computer we have in this doghouse on the command center, where we say auto track hold 91 degrees inclination. It sends that electrical information or whatever to the BPA. The BPA has a small flow diversion and can create those pulses that are sent down hole. So it's all done for us now. What we sell this to operators is we say we take out the human error. So I wasted the company's time when I was on the rig floor down because I screwed up or got scared or nervous or whatever. And you know, that caused additional downtime. With this, it's faster. We can do it on the fly. You don't have people going up to the rig floor. Why would the operator like hearing that nobody has to go to the rig floor to down? It's number one. Perfect. So you can see here there's operational modes, there's steer mode. Our tool has 3 main modes. I told you that inclination hold mode. We tell the tool just to lock in, drill it, hold this inclination as we drill in. We have steer mode. This is usually what we use to build a curve or do a trim. We tell the tool a direction and force to steer. So if you're doing 100% build, you're going to say 0 at 50% steer force. You can go up to 100, very rare. But you're basically every stand or every 90 feet or every 45 feet, depending on what kind of drill pipe you're using, you will change your commands and drill a hit based on what you're seeing from your survey measurements and your bid information. Now this is whole motor inclination